wanted to quickly gloss over this entire thing so you will be able to easily explain BJT amplification tomorrow. Now, one thing you have to consider here is what is a BJT? BJT, it's simple. It's simply a P and N junction where you either add a P region here and heavily dope this side, which will cause it to be a PNP BJT, or likewise, you can also add an N region here and heavily dope it to make it an NPN BJT, right? This is very simple. It's just a P and N junction with either an N region or a P region added to one of its end, and you're heavily doping it, which essentially, and heavily doping is important. Why? Now let us consider a PNP junction for instance, okay? And if I'm heavily doping it, there is more amount of holes here. Now, since there are more amount of holes here, that is when I can transfer the holes here, no? And essentially transfer it here, and there's unidirectional flow of current. I'll help you visualize that better. Now look at this PNP junction. This is essentially a PNP junction. What will you notice here? There is one region which is heavily doped, which is called the emitter region. Fine. One region, the other part of it is called collector, and the middle one is called the base. As simple as that. Sweet. Now, one thing you have to consider is within a BJT, there are two junctions. Correct. Now, this is emitter and base. Now, between emitter and base, you see there's one junction. This is called the EB junction. And you notice that between the base and the collector, there is one junction. This is called the BC junction. There are two junctions, correct? One junction, two junction. Now, let us consider this. Now, this is wrong. This should be like this, okay? Now, let us consider this. We will consider two configurations. We will consider this one. First, let us only consider this part. When I consider this part, what do I notice? I notice that this is now a PN diode. Let us forget this exists, okay? Only PNN exists. This is forward biased. Now, why is it forward biased? Positive end is connected to P, negative end is connected to N. This is forward biased. Why does it have to be forward biased? Because if it is forward biased, the positive charge, this has relatively more negative charge, this has relatively more positive charge. Since it has more negative charge, it is essentially able to pull holes towards itself. As simple as that. Okay. And the current, there is an IB current which flows. Okay, IB current flows outward. In the case of PNP junction, there is IB current. IB current is going outside. This is called the base current. It's moving outside. If base current is moving outside, now you have to understand that the conventional current is this, then the electrons will go into the base. The holes are going outside, the electrons are going inside. This happens when you do a forward bias. Now why is this important? If the holes are going outside, then a concentration of holes is even lesser, which means more holes can enter the base, which is good. And I will explain how electrons entering is essential later on, but for now you understand that we need to set this in forward bias. In the same manner, I will consider this section. Okay, now when I consider this section, this is positive is connected to this N region and negative is connected to P region. If positive is connected here, if the base is more positive than the collector, if the collector is more negative, obviously it will pull the holes because it's more negative. So it has to be connected in reverse bias configuration. Sweet. So this BC should be in reverse bias and this EB should be in forward biased. Okay. EB junction forward biased, reverse this BC junction would be in reverse biased configuration. If this configuration is met, holes will be easily able to move through this entire system unidirectionally. IB current is going outside. Why? Because holes are going outside, meaning holes can enter easily. As simple as that. Sweet. Now I will essentially try and give you the feel for amplification here. Now consider this. Sweet. Now this is a symbolic representation of an NPN junction and a PNP junction. Okay. What is different here? In a PNP, we just discussed PNP, okay? What is happening in PNP? The conventional current will enter the emitter. But in NPN, the conventional current will enter through the collector. This is what is different. Now, if the conventional current is entering to the emitter, it will exit through the collector. But here in NPN, it is exiting through the emitter. the conventional current. So it is basically the opposite of each other. Now what is happening to the base current? In PNP, base current is going outside, but in NPN, base current will go inside. Okay, do you understand that? It's just the opposite of each other. This is how you represent this. Now one thing you have to consider is, imagine this configuration. Okay, now in this configuration I am basically setting up a voltage between emitter and base. VBE voltage I'm setting. Sweet, nothing I'm doing, I'm just setting VBE voltage. When I set VBE voltage, what happens? This becomes forward biased. Now if this becomes forward biased, there is essentially transfer of current from emitter to collector, correct? I can also do this. It will not change anything, but this setup will basically cause forward bias, and it will basically produce IB current. Okay, so VB will produce IB current. A small change in this IB current will drastically affect how the emitter to collector current is essentially flowing. So I can, by tweaking VB value or IB value, change how much current will pass from emitter to collector. Okay, it acts as a variable resistance here. No, this is why a small amount of current can drastically affect a much larger amount of current from emitter to collector. This gives you some feel of that amplification factor. I will elaborate that in a moment. Let us consider PNP junction only. Before we go though, I will just summarize what we have done. See, in NPN there is transfer of electrons, but in PNP, as we have discussed, there is transfer of holes. Correct. Now, conventional current we just discussed. Conventional current flows into the collector, into the collector, and what in NPN it flows into the collector and exits the emitter. Okay, out of the emitter. But in PNP, it flows through the emitter. No, it flows into the emitter and out of the collector. It's the opposite. Biasing is important. See, in the PNP, the emitter should have the highest voltage, positive voltage. The next it's base and collector. So basically, collector should have the least positive amount of voltage. Why is that the case? Now see, I will bring that up here. Now here, if this is collector, right? The collector voltage should be less. This is positive, it should be positive. Why should the collector voltage be positive in PNP? Is because we are essentially, no, so this is emitter. Now the emitter voltage should be high in PNP. Why? Because it should be more positive. Basically VE should be more positive than V base, correct? Why? Because we want it to, because then only the forward bias condition is set between these two, and holes will be pushed into the base. Similarly, we want that the V base voltage should be more positive than V collector. This is collector now. V collector voltage. Why? Because we want the base to push holes into the collector. This sets up the reverse bias condition. So this is summarized here. The emitter should have more voltage, more positive voltage than base, and base should have more positive voltage than collector. Vice versa in NPN case. Okay, we use NPN more because electrons have higher mobility. Electrons have lesser mass, so they have higher mobility. Okay, so we use NPN transistors more than PNP, but we also use PNP if we want to sort of have that reversed bias polarity. If you want opposite polarity, we use PNP transistor. I will go to these conditions. These are not very important at the moment, but I will give you that feel of amplification. Okay, now here's the thing, a few factors you have to consider. When I'm considering current, how is current flow really happening here? One second, we'll just erase that part. How is current flow happening over here? You will notice that IC current is essentially entering from here. Now this current is IC current. Okay, collector current. If current is coming like this is emitter current, sorry, this is emitter. Now if emitter current is coming like this, and emitter current, this is okay, sweet. So if collector current, this is collector current now. If emitter current is coming like this and it is producing IB and ICE, what is essentially happening? This is one node. Imagine this to be a node. Okay, if this current is entering this node, then the current leaving out of these two nodes should sum up to give this current. Exactly, right? So IC current here is basically the sum. No, IC, okay, no, the IE current is the sum of these two currents, correct? IE is the sum of IB and IC. So what is IC essentially? IC is basically IE minus IB. That is what we have written here. Sweet. So we get this relation. Now current transfer is a ratio. Current transfer ratio basically is the collector current divided by the emitter current. Usually this is equal to 1. What this means is the current received at collector is the same current which is entering the emitter. Usually this is 1 itself. Current gain is what is important because this will directly relate to amplification. Current gain is telling how much change in collector current is happening from the change in base current. Now we've talked how varying base current even a little bit is basically changing how much current passes from the emitter to collector, correct? That is the IC current. See, essentially this is IC current only, no? So this small change is basically determining how much current transfers from E to C, emitter to collector. We are measuring this as a ratio from current gain. Beta is the ratio of how much current will increase, collector current will increase by varying IB value. Okay, we have discussed that here. How varying a small amount of IB, a small amount of IB here, if we vary, how will that change the amount of current that is moving from emitter to collector? IC current, how much it is changing. We measure that through beta. Okay, beta is basically equal to IC divided by base current IB. Now, these are other relations you can keep in mind. Just go through them. You don't have to, there's no particular significance. But we have gone to this. I've already told you how alpha is the current transfer. No, current is usually, transfer is usually 1. That is the current entering the emitter is the same current leaving the collector. So it's usually 1. Beta is what is important. Okay, and typically the value is around 100 or 300. It can be anything. What this essentially means is um, you'll get this relation basically, man. See, beta times IB current is basically equal to IC current. So more beta, if beta is like 100, what happens? Even if I slightly increase IB current, IC is increasing dramatically. But if it's 300, then the factor is even more. It's increasing it even more slightly also, I will still increase IC by a lot. So this relation is what is important. Beta times IB equals the collector current IC. Okay. I want to give you this sort of understanding. Now, when we consider now IB is base current. Now, base current is affected by a number of factors. What are these factors? Base current, this is P and P. Okay, for instance, base current is this. What is base current affected by? This is IB. Now, IB is affected by the recombination rate. Now, if more number of recombination is happening here, okay, more IB has to be done here. Why? Because now to understand this, you'll have to go through the logic behind this BJT amplification. See, within now BJT has three regions. No, it has a P region, it has an N region, and it has another P region. Between all these three regions, the amount of charge should always be in equilibrium. So the number of positive charge should be equal to the amount of negative charge. Sweet, very easy. If that has to be preserved, positive charge have to be equal to negative charge, and this equation has to be sustained. Okay, here it is hole concentration, this is electron concentration, this has to be equal to 0, and if there is any donors, their sum should also be equal to ionized donors, their sum should also be equal to 0. So essentially in P region, N region, and P region, again the charge should be net 0. The positive charge should be equal to the negative charge at any given time. This is called the space charge neutrality principle. This is important because now see, I have talked about this relation, you know already. No, collector current by base current is equal to the beta. Beta is what again? The current gain ratio. Right, we've discussed beta here. Beta is the current gain ratio. Sweet. So this is also equals to, this is equivalent to this expression. What is this expression? TP is the average time between recombinations. And TT, what is TT? TT is the time it takes for the carrier to cross the base. This is important. Why is this similar to the current gain ratio? Why is this similar to this? It's because, if now imagine that the amount of time it takes to recombine. See, in this PNP junction is there now. I'm transferring holes. Now holes have entered here. Now once holes have entered, what happens? This becomes more positive. The N region becomes more positive. But from charge neutrality, we know that charge needs to be balanced. If charge needs to be balanced, but there's more, there's a hole added, then we know IB current goes like this, na? If conventional current goes like this, electrons is entering. You see the point? So if electron enters, one electron comes here. Okay. So what happens in the end? There is an N region. Holes has been transferred. So there's one hole. And since there is a hole, charge neutrality has to be followed. So one electron will also enter. Okay. Now this base has one electron, one hole. Sweet. Now, will they recombine? No, they won't recombine. The base is very narrow. The recombination rate is very less. So the hole will simply go like this. Okay, first time. Now another hole will enter. Another hole might also simply go like that. Now the third hole might enter. Now the third hole which enters might recombine with this electron, and it becomes it's basically, again, it's neutral, it's all done, nothing transfers. Now another hole will go, and again one will be injected because new hole comes. Now the time it takes for the holes to recombine with the electron. Now, if the recombination time is very much, it means that only one electron entering here can basically ensure that more number of holes can be injected and transferred. It ensures more transmission, okay, more transits of holes. If the recombination rate is high, if the transfer rate of the carrier is very low, what happens? That means holes are able to transfer very fast, more faster than it can recombine. So it transfers, and at some point the recombination rate will hit and it will recombine with the electron, and new hole will come. Since new hole is there, again charge neutrality, so another electron will enter because the previous electron was recombined. But what you will understand here is one hole is even just one hole, even one electron, sorry, even one electron is able to transfer many number of holes. It's not just one hole. It's not like it's recombining with every hole. Recombination rate is very less. So even one electron is able to transfer many number of holes. Okay, this is why it is important. And this ratio will essentially give you the same equivalent here. It will give you how much current each electron is able to transmit. It is basically the recombination rate divided by the time it takes for the carrier to move across. It's the current gain ratio. Typically it is 10 microsecond recombination rate, and the time it takes for the carrier transmission is 0.1 microsecond. Beta is usually around 100. Sweet. This analogy gives you a lot of depth because now see, as we have already discussed, each injected hole creates a local positive in the N region. Since local N region local positive is there, neutrality has to be sustained, so electron is supplied to the base, or charge current goes like this, so electron enters. Okay, since electron is supplied, it doesn't recombine directly. It allows multiple holes to transmit. Okay, supports multiple hole transits during its lifetime. Okay, now this is considering that the transmission, that TT is very less than TP, which means that the transmission time it takes for the carrier to move across the N region is very less compared to the recombination rate. If this is fulfilled, it means that it is able to transmit many number of holes. Even one electron is able to transfer many number of holes. But if TP is smaller, then as soon as the hole enter, it will recombine with that electron following charge neutrality. No, there's no transfer. That is why the what do you say, recombination time should be more. It should be increased. How do you increase the recombination rate? By decreasing the size of the, or the width of the base. I will get to that in a second. Now, there are different kinds of configurations for the PNP junction. Okay, before I enter that, we will cover this section. IB current is affected by about recombination rate. Now if recombination rate is high, It basically means more amount of electrons has to enter to again neutralize the charge. So recombination, more recombination means more IB. Okay. Injection. What is injection here? Electron injection from base to emitter. Now we know that it's usually forward biased. Okay. Which means holes will go like this, but sometimes holes might go like this also, rarely. If that happens, then it's called reverse injection current. That will basically reduce the IB current. So that is why it's no, that will actually increase the current. It will increase the current, so because it's going in the opposite direction now. We have P and N and P. If it goes like this, if it goes like this, it basically means another more current should go like this again, right? So this, an electron is being injected over here, which means another hole becomes here. If another hole occurs here because an electron is transmitted or injected into this from base to emitter, then another hole must go over here because there is another hole created here. If electron goes like this, a hole is created. This new hole has to go out. If this new hole goes out, there is more IB, no? That is why injection will again increase IB. Thermal will decrease IB, okay? So I recomb plus I injection minus I thermal will equal to IB. These are the factors affecting IB current. You don't have to worry about injection efficiency. It basically tells the amount of in PNP junction, the amount of holes it is transferring. Now this can transfer both holes and electrons. Why? Because a PNP junction, in a PNP junction, P basically mostly transmits holes, but a BJT can transfer both holes and electrons, right? So if it transfers electrons, then the emitter injection efficiency is less, but usually it is one only, which means the amount of electrons it's transferring is negligible. It's mostly just the holes which it's transferring. Okay, base transport basically means the carriers which are collected over here is the same amount of carriers which is injected here. This is equal, and usually this is also one. Current gain can also be calculated by the injection efficiency times the base transfer factor. This is another formula. You can remember that if you want to, otherwise it's not very important. And we'll have to consider this fact. See, when you look at this, right, these are three different configurations of a BJT. Sweet. This is common base. This is what is this? This is basically it's a common base array. This is what we were dealing with. This is emitter, collector. This is base. This is what we've been discussing so far. Okay. And there is a VBE which is set. Okay, if we establish a VBE, it will basically transmit and there'll be an amplification. Holes will transmit or electrons will transmit respectively. But over here, it's an emitter is down. Okay, so it will basically become VEB. So there's an opposite effect here. If we increase VEB, then instead of more current happening, it will be less current happening. It will have an opposite effect here. Here it is VBC. There's a very interesting discussion about what happens if you add VBC. I will bring that up in a second, but these are three separate, this is common base, common emitter, common collector, three different configurations. Okay, common emitter, common base, common collector. What we have been discussing about is common emitter. We have been focusing on sorry, actually, this is VBE, sorry, this is B now, this is VBE, this is VEB. Okay, it's the same thing, but it's the opposite. We've been focusing on this so far. Sweet. Um, what happens here? Input is, we've talked about the input. Input is basically over here. Okay. And we establish a voltage between V, B and E. We've talked about this. We establish a voltage between base and this. If we establish a voltage VBE, forward bias will happen and basically holes will transfer here. Okay, as simple as that. Very easy. But VEB mein what happens? It's the opposite. So more VEB means less current will transfer. Less current will actually transfer from here to here. This one we will discuss in a second, but you'll notice. So emitter mein the current gain is very high. Okay. But in common base, which is the opposite of it, current gain is very less. Okay, it's not very much. It's pretty limited. There's no current. There's not much current gain, and the current transfer is also less than one. The current which is transferring is also less. Now, this common collector, we'll talk about it later. But you can look at the three different cases. They'll have different configurations, different impedance. I can talk about impedance, but don't really need impedance as of the moment. So maybe we'll come back to it in a bit. But let us go to something more fun. Now, this is common emitter. This is the same thing we've been discussing so far. Sweet. What happens now when I establish VBE? They have established VBB. Okay, this is a DC source, correct? There's a VS. This is the actual source input. This is now input is this is emitter. It's a common emitter. It's basically the normal common emitter amplifier. This is emitter, this is collector, this is base. Okay, what did we discuss then? If we basically set a voltage between this and this, base and emitter, VBE, if we establish this, if we establish there is forward bias. If there is forward bias, there is transfer of current from emitter to collector. As simple as that, right? But these are some of the equations you have to consider. Why are we considering VBB? VBB is a source. If VBB is not there, you can also neglect it. It will simply be VBE and RB. But let us assume there is a VBB. Then we have to subtract VBB by this voltage which we already established, divided by RB, the resistance of this base. And VB here, typically the voltage you will give, the bias you will do between base and emitter is 0.7 volts. This is what they've mentioned here. And if we do that, we will basically get this relation. We will get this relation was what we previously had. No, IC is equal to beta times IB. This is the equation. We have got this from current gain ratio, IC by IB, right? VCE here, what is VCE equals to? VCE, this is important. This is another thing we have to consider. Now I've told you so far that we are considering, imagine this now. I have told you so far that this is emitter, this is base, this is collector. I've told you we're setting a voltage here, VBA. This will basically create forward bias and transfer current, correct? But there is also another voltage set between collector and emitter called VCE. This is very important because VCE, the VCE voltage will directly determine how much the switching operation and everything. We'll get back to that as well. But you'll have to also consider that this is a VCE voltage. Now VCE voltage and this is equal to what? VCC. Where is VCC here? VCC is this main voltage. Some voltage is lost here, which is equal to ICRC. Okay, we subtracted ICRC, VCC, that will simply get VCE current. Okay, if we take this subtracted with this, it will give us VCE current, VC voltage.